The next lecture is going to be on natural resource use. That is, what we use, how we use it. Now, any kind of resource use, any kind of use of energy, there's always a trade-off. Um, how much, how much are you going to be able to do with this resource? Um, is the cost of extraction and processing worth the ultimate cost of what you're able to use with it? Is the pollution caused by the use of this resource, is this worth the cost of whatever activity you're doing, or worth the long-term costs of it? Pollution um, is a byproduct of resource use. Some of these products have more pollution than others. Some products produce more energy than others. Some are more efficient than others. But regardless of what you use, there's always a trade-off. There are a couple of definitions here. Resources. These are naturally occurring, exploitable materials that society believes is useful. In this case, exploitable simply means something you can use. Something you can use. Something's useful to the economy and your material well-being. Now, renewable resources. Renewable. Some things can be recycled and used again. These are materials that can be replaced or by natural processes. Or can be replaced within a reasonable time frame. Oil, it is being produced by natural processes, but it takes millions of years to produce. Suppose all the oil in the world was used up. Could it be replaced in another million years or so? Technically, it would be replaceable, but not in a useful time frame. But something like, say, sunlight and wind power, that's always going to be here. It's always around. It can always be used. It gives perpetual resources. Perpetual resources, these sources that are virtually inexhaustible. That includes wind, solar, tidal, um, and so forth. Yes, tidal energy, the tides of the oceans, that can be used as energy. Because remember how electrical plants work. Basically, it's turning a turbine, and that turning of the turbine produces electricity. Now, what do you get it to turn that turbine? Um, Sometimes it's like a simple engine, internal combustion engine. Gasoline power makes the engine turn on its own. Sometimes you can get wind power to turn that turbine. Or, say, the example of solar power, skip the turbine process and just turn it directly into electricity. The tidal power, the constant in and out of motion of water, that can be used to turn turbines underwater. Steam power is very often used to turn turbines at a very rapid rate. But the thing is, what do you get to turn water into steam? You need some kind of power source to do that. Now, you have perpetual resources and you have potentially renewable. This is renewable if left to nature, but can be depleted. Examples: this forests, groundwater, plants, and animals. They are renewable if left alone, but use too much of it, and you clear cut the forest, it's gone forever. Groundwater sources can be depleted. Plants and animals, they can be pushed into extinction. But groundwater can charge itself over time. Forests, cut down a couple of trees, they can grow back. It just takes a while. You've got non-renewable resources. These exist in limited amounts or generated in nature so slowly that supply is finite for practical purposes. Amounts or produced slowly in nature. Again, an example of that: oil, natural gas, fossil fuels. Produced by nature, but very, very slowly. At least too slow for our uses. Certain types of minerals. There are only limited amounts of them. So forth. Now, while minerals can't be entirely destroyed, their usefulness can be diminished, and sources of unused materials can be depleted. For example, uranium can be used as the energy from uranium can be used as a fuel source to power nuclear power plants, but they're only useful for a certain period of time. So basically, their spent can't be used anymore. But many minerals can be reused. Aluminum, lead, zinc, diamonds, those can be reused. Oil sometimes can be reused. It can be recycled for different kinds of uses, certain limited types of uses, but sometimes it can be recycled if it's not thoroughly contaminated. But remember, all this is defined by usability, and that definition changes with our changes in technology and changes in the economy. How we use resources, um, that changes over time. Our need for certain resources, that changes with time and technology. Um, that idea of improved or usable resources. That is, this is the quantities of a resource that can be extracted profitably from known deposits. Example, oil in South Arkansas. There's hundreds of millions of dollars of oil sitting beneath our feet, but not a lot of it can be gotten to fairly easily. The natural gas pressure that pushes up oil towards the surface when you're drilling for it, that supply has been depleted, so the oil that's remaining is hard to get to. Can it be gotten to? Yes. Can it be gotten to and still make still make money off it? Debatable. Now, all this comes down to the idea of energy. Energy, as quite simply defined, is the ability to do work. That work is defined a lot of different ways, in horsepower, wattage, and so forth. But the different types of energy, potential energy. Means I hold up a marker. The force of gravity is pulling on it. That energy between what I'm holding it versus the force of gravity, that's potential energy. But you drop it, the motion, that's kinetic energy. Just in motion. Chemical energy. The energy from chemical reactions. Rockets using explosive liquids. That is a type of chemical energy. The energy used in your car, gasoline, that is chemical energy. Biological energy. Use of animals or something they call biomass. That is biomass. The decay process of certain biological materials, the gases and heat produced, it can be used as a power source. And then radiant energy. Glow in the dark stuff, radioactivity. Uranium and other radioactive materials for nuclear power plants. So potential, kinetic, chemical, biological, radiant, those are all potential sources of energy. All this is defined by the law of conservation of mass and energy. The law of conservation of mass is mass can be neither created nor destroyed. Same thing with energy. It can neither be produced, created, nor destroyed. But it can be transformed into different things. For example, your potential energy here. Drop it. Energy is not lost. It's simply transformed from potential to kinetic. Law of conservation of mass. Mass is always still the same, just to transform to something else. Through various chemical reactions and so forth. Or if you go with Einstein's famous equation E equals mc squared, yes, mass can be converted to energy, particularly in nuclear fusion reactions. Mc squared. Conversion of mass to energy. It's what happens in thermonuclear blast. Also happens when the sun shines. Energy, mass transformed directly into energy. Now, energy can be extracted in a number of different ways. But new energy sources have changed technology and have in turn changed society. Use of electricity, for example. That was a new technology, and that in turn changed society, changed the way we live. We think in terms of nightlife now. Think in terms of staying up all night because we have electric light. Domestication of animals, using the physical energy of animals to do work, draft animals. Cows, horses, donkeys, particularly, they're used as draft animals. They can pull plows, so they can pull goods and wagons and so forth. They can move things a lot better than a lot faster than humans can. Wind power. Learned how to harness the power of wind, and that in turn learned how to use that to propel ships, old wooden sailing ships, those big sails that would push the ships along with the power of wind. Windmills, very popular on farms, iconic feature farms. They would be used to draw water up from underground. And now wind power can be used to generate electricity. Chemistry provided all sorts of different new uses for new sources of energy, which in turn changed society. Gasoline for the automobile, particularly. Now, the Industrial Revolution in the 18th, 19th century is noted for a shift from renewable to non-renewable resources. That is particularly the use of fossil fuels. It's always existed for a long time. People knew what oil was, but they finally found a use for it. A use for oil beyond simply lubricants. It can be used as a source of fuel. And particularly, we designed engines and other devices that ran off these different kinds of fuel. Now, this in turn has led to increase in personal wealth and gross domestic product of countries. But a good portion of the world, though, still relies on wood for heat and cooking. Years ago, I listened to a speech by Jimmy Carter when I was at the University of Texas. This is the 1990s. He said, for most of the Western world, the word for today, that is the 1990s, was technology, the most important word of the time. But for most of the rest of the world, the most important word is firewood. That is, given our technology, we think in terms of low technology, we don't have to worry about where's our heating or cooling coming, where's our light coming from, how are we going to cook a meal? Because we have the resources so readily available that we can use it anytime we want. But in many parts of the world, still, how you eat tonight is going to depend on how much firewood you can get. Well, it depends on how warm you're going to be at night, as be how much firewood you're going to get. Now we get to oil. This is 40% of energy used in the world. And non-renewable resources like wind and solar are starting to change this equation. Oil is still used quite widely. And oil has a lot of important uses. It's used in waxes, in lubricants, in plastics. Many plastics you use are oil-based. Fuels, gasoline, rocket fuel, jet fuel. All of those are based on oil. But even if we stopped using oil as an energy source, as a fuel source for gasoline and so forth, and jet fuel, there's still a lot of other uses it can be used for. It'll probably continue that way for quite a while. But let's let's look at total production. Biggest producer in the world, Saudi Arabia. There's 11.8% of the world's oil as of 2005. Consumption, leading consumer, United States, use about 25% of the world's oil. To Russia, 0.7%. The problem for Russia is most of this fuel is oil profits are not distributed around the country. It's kept by a very select few, the oligarchs who basically control everything. So even though it's an oil-rich nation, particularly in the Caspian Sea area, most of the country hadn't seen the profits from it. User, China. Moving up fast. Our largest producer in the world, the United States. We're a big oil producing country. At 10% of the world's oil. Third largest consumer of it, Japan, 6.9%. Mexico, big oil producing country. At 1/20th of the world's oil, 5%. Germany, fourth largest user. Russia, actually the fifth largest user. Other large producers, China. They found some oil reserves, 4.8%. Iran, 4.7%. Norway, a lot of oil production in the North Sea, 4.4%. And Venezuela, 4.3% of the world's production. So oil can be found in many different parts around the world, but again, the problem is how do you get to it? Is it accessible? A lot of different techniques these do that. Fracking is one of them, basically pumping water into the ground, trying to force the oil up, basically changing the pressure, underground pressure. Some of it is by liquefying certain types of coal into oil. But oil is found extensively across the Middle East, but also the United States, parts of Canada, Mexico, Venezuela. It can be found in many different areas. It can be found offshore. On the Gulf Coast, there are a lot of offshore oil rigs, basically drilling into the under the ocean surface, under the ocean floor to access the oil there. But in the 1970s, the domestic supply began getting more expensive to extract and consumption was rising steadily. So we started buying more and more from the Middle East, one of the most unstable regions in the world, between 1970 and 1977. On those came the rise of OPEC, the Organization of Petroleum Exporting Countries, OPEC. 11 oil exporting countries, including Venezuela, Nigeria, Libya, and various countries across the Middle East, including Saudi Arabia and several of the Arab Gulf states. So we became more dependent on Mideast oil, which meant since the Middle East, OPEC is largely controlled by the Middle Eastern countries, meant that the United States was largely becoming more dependent on foreign sources and foreign powers for our energy use. Some protest certain American policies. There are a couple of times in the 1970s that the OPEC decided they weren't going to sell oil to us. Also, what they called the oil shocks. Caused a panic along lines of gas stations. People feared that we were going to be out of oil. So these oil shocks came to 1973 and 1974, and from 1979 to 80. But these oil shocks were soon abated in a short time because while OPEC was not selling oil to the United States, they were selling oil to our various trading partners, and we bought the oil third hand from them. But the problem of oil importation began rising steadily. In 1982 and 1986, U.S. imported 31% of its oil. But by 2002, that increased to 60%. Most of our oil was imported. It's very dangerous, man. This is just right after 9/11. We're now at war in Afghanistan and about to go to war with Iraq, too. And they had a lot of very powerful allies in that region that controlled our access to oil. Recently, there was a push to try to move away from imported oil, which led to, by the early 21st century, more oil companies pushing for fracking. Therefore, by increasing the amount of oil yield, the amount of oil that can be produced and sent to market in the United States. But ironically, in the midst of all this, though, is the United States, by into the first decade of the 21st century, we were a net exporter of gasoline. That is, we brought in a lot of oil, we sold and produced that into gasoline through various refineries we had in the United States. Most of that, a good portion of that, we end up sending out and selling around the world. We're importing oil, but selling the gasoline out of it. Now, about 1 trillion barrels of oil are thought to be proven reserves. Maybe 900 billion more is undiscovered. There's a lot of oil out there. It can be recycled in some limited ways, but as a fuel, not sure yet. So that has been the push for conservation, really since the 1970s with the first OPEC oil shock. There's a drive to make cars more energy efficient, so fuel they do have lasts longer, better mileage. And also moving away from being so heavily dependent on oil to other sources of energy. To be pushed towards solar, wind, and so forth. At current rate of consumption, maybe have 50 years of oil left, but again, we adapt. Learn how to extend our oil sources, learn how to better manage it through fuel efficiency and so forth, and offsetting it with alternative sources. About 30-35% of oil in reserves in the United States can be recovered. That is, it can be extracted and sent to market. But a lot of it can be. And that's going to be the difference that how we learn to extract it. That could be a part of it, what drives the conversation on energy use in the United States now from this point forward. New technologies, I believe, might be able to make most of this moving from about 30 to 35% to 60 to 70% recoverable. That is managing to double it. But again, the cost behind it. Oil, while it is very useful, it is a highly pollutable substance. It causes a lot of pollution extracting, a lot of oil spills. Oil contaminates the water supplies and the ground. That causes a lot of problems. When oil is used or combusted, it produces a lot of carbon dioxide and carbon monoxide. Carbon carbon dioxide, which large amounts adds to the amount of greenhouse gases in the atmosphere affecting the climate in the long run. But another source of oil, source of energy, another fossil fuel, coal. The United States produces a lot of coal. 1850, 10% of American homes used coal in some form. By 1910, about 80%, used mostly in furnaces and so forth. It wasn't just in the north where they're using furnaces for heat, but also even here in the south. The old administration building, when it was built in 1905, there was a big coal-fired furnace in the basement. The students that actually would actually shovel coal into that furnace to heat the building. And coal is also used to fire up steam engines and also to at the factories as well, particularly in the production of steel and things like that. But coal was the most important energy source in the United States until 1950, when other more practical forms were found. Coal, it's a highly polluting substance, sends a lot of dust and fossil fuels into the air. But it can be found, but oil and coal, it's found in different parts of the country. The thing about coal is there's different kinds of it. Certain types of coal in certain parts of the country, they have different what we call specific heats. That is, the kind of coal it is, it's capable of producing different amounts of energy. Lignite coal is the most common form of coal west of the Mississippi River. There's actually some coal mining in Arkansas, also in states like Colorado, Wyoming, New Mexico, Utah, and so forth. Lignite coal. Lignite coal can also be transformed into oil. Anthracite and bituminous coal, that is most commonly found in the Northeast, Kentucky, West Virginia, Ohio, Pennsylvania, and so forth. In the United States, there's potentially 240 billion tons of oil that's potentially mineable. Leading producers of coal in the world are the United States and China. But in recent years, there's been an effort to try to phase out coal use entirely, try to shut down power plants that use coal, go towards more cleaner burning sources, cleaner sources of energy. Now, coal use was steady between 1990 and the early 2000s, but a lot of rising consumption in parts of the developing world, particularly areas like South Korea, Taiwan, and India, Indonesia, and Japan. Then you've also got natural gas. Natural gas is mostly methane. CH4, simple hydrocarbon. A hydrocarbon is defined as any substance that defines carbon and hydrogen. CH4, methane, among the most common. Generally, though, those chemicals ending with A and E, they are hydrocarbons, can be used as certain fuel. Methane, pentane, octane, particularly fuel, and so forth. Now, methane, it can be cleanly used, but like other fossil fuels, the byproducts are carbon dioxide of water. Carbon dioxide being a fossil fuel, being a greenhouse gas. Now, burning natural gas, like I say, these products are produced, but it is relatively fewer greenhouse gases and other byproducts than you have, let's say, coal or oil. Cleaner, but still not entirely clean. Now, the United States in 1900, natural gas was about 3% of the world's supply. % of our energy in the United States came from natural gas. Now, originally, natural gas was considered a waste product of oil extraction. How they do in the oil fields in West Texas, and around Odessa and Midland, is so much that natural gas being used. What they do is they just they burn it as it comes out of the ground. So at night, sometimes you can see all the, even on satellite images and driving down the road, you can see quite a bit of light just from the natural gas being extracted and set on fire. By 1980, it was about 30% of American oil, 30% of American energy usage. 30%. About 2000, it declined a bit to 25%. Of course, the thing about methane and natural gas is it is poisonous to breathe, obviously. So there have been problems with natural gas using appliances like stoves and certain heaters that sometimes are some very slight leaks over time. And that can cause a health problem. That's why I've been pushing the last couple of years for much more efficiency in these. Even the idea of getting rid of natural gas stoves altogether. Natural gas can be a problem if there's a leak in the pipeline leading into the house. Can lead to carbon monoxide poisoning inside the house over an extended period of time if there's a small leak in that pipe. But natural gas is used extensively in many homes as a heat source during winter. About 2002, globally, about a quarter of all energy usage was from natural gas, 25% worldwide. Again, natural gas is used most commonly in heating and cooling homes. About half of all homes in the United States do use natural gas still. Sometimes it's used in power plants. For example, the Panda plant here northeast of El Dorado, that is a natural gas power plant to produce electricity by combusting natural gas. The heat produced from that turns the turbines, which produces electricity. Now, shipping gas by sea requires cooling it to a liquefied state. Liquefied natural gas is down to about minus 260 degrees Fahrenheit. Liquefied natural gas. It's pretty chilly. While it can be transported across seas, it's just easier to use a pipeline. And so, therefore, most of it is transferred by pipeline. Now, proven natural gas resources worldwide, Russia has 31% of it, the Middle East 36%, and all the others between 4 and 8%. And Russia and the Middle East having most of it. Nuclear energy. Now, nuclear power plants, they use fission energy, nuclear fission. Is by splitting uranium-235 atoms. P35 is its atomic weight. It's number 92 on the periodic table. And basically, not just splitting it, but shattering it. So there's a lot of energy produced, but also a lot of waste byproducts of radiation. It is a very powerful source of energy. 1 pound of uranium-235 has the same energy as 5,000 barrels of oil. United States and Canada, that's between 15 and 20% of our energy use is from nuclear sources. Japan, they have dozens of plants, use it, provide about a third of their energy. But because it is dangerous, and there are a lot of waste byproducts, some countries are very hesitant to use it. For example, Denmark, Australia, New Zealand, they're considered to be nuclear-free countries. They work very hard to avoid use of nuclear power. But no new nuclear power plants have been built in the United States since 1978. A lot of fears avoided with it, associated with nuclear power. And if nuclear power plants are not managed correctly, the accidents could be devastating. In 1986, for example, see what happens at Chernobyl. Badly managed, badly designed plant explodes. Could easily have left most of Western Russia and Eastern Europe uninhabitable. But as it is, the city around it is be uninhabitable for centuries because of the radiation in the area. But nuclear fission, it is in a power plant, basically, is a giant water heater. Just like natural gas plants and coal-fired plants and so forth. That is, the heat from nuclear reactions warms the water, turning into steam, and that steam pressure then turns the turbines, which then in turn produce electricity, which is sent out across the power grid. Same thing with natural gas, same thing with coal, so forth. Even gasoline powered plants, same principle work. And nuclear fusion, a lot of power. It's a lot cleaner than a nuclear fission. A lot more energy efficient. There's a lot more bang for the buck. This process uses the sun, basically, instead of splitting them apart, it's bringing them together, smishing them together. That releases a lot of energy. It's the process that powers the sun and every other star in the universe. Basically taking 4 hydrogen atoms and they produce 1 helium atom and a lot of energy. And all because of usually MC squared. Helium, it's two protons from the original 4. But what happens, these other 2 hydrogen protons in the process, they are transformed directly into energy. Law of conservation of mass and energy is preserved. That mass still exists, but is transformed to something else. In this case, a lot of energy. And that supply in the sun is available for billions upon billions of years still. But could we use it on Earth? Not just sunlight, but reproducing nuclear fusion? Yes. Now, the thermonuclear bomb, that is an example of a runaway nuclear reaction. But could it be controlled? A lot of experimental reactors are producing minute amounts of electricity, but so far it isn't quite practical yet. Very close to breakthroughs on it. Research continues on it, but if nuclear fusion is achieved, it can completely change how energy is produced and used around the world. Just as gasoline changed how produced and used around the world when it first became available. Now, the main sources of fusion would be, for example, water, H2O. Hydrogen produced into helium, oxygen left over. And just 1 cubic kilometer of ocean water, it's 1 cubic kilometer of it. Very tiny, tiny fraction of the amount of water in the world today. That could supply all the world's energy uses. Let's turn that 1 cubic kilometer of water into energy, fusion energy. It'd be an inexhaustible energy source if we're ever able to use it. Biomass, which we talked about earlier. Any organic material produced by plants, animals, and microorganisms that can decay. And therefore, this decay process, it can all be transformed into fuel. Hydropower, the power of the motion of water. Tidal power, for example, but also water running down rivers. A lot of reservoirs, and how rivers are dammed up at one end and lakes filling in behind them. These dams are often hydroelectric plants that is they let a little bit of water through. And that water pressure turns the turbines, which produces electricity. Norway, 99% of their energy use comes from hydropower. Solar power, the energy from the sun, you have different types. You have passive solar power, which uses the energy for heat. In Israel, about 2/3 of the houses are heated by solar energy, passive solar energy. Then you have active solar energy, which is photovoltaic cells, solar cells, which take light, any kind of light, and transform it into electricity. Increasingly becoming a popular source of power for homes and for businesses. Many areas they have what's called solar farms, just rows and rows of solar panels, enough to power a small city. Geothermal energy. Geothermal energy, basically water warmed steam by the earth. Steam below the surface, it's being pushed up, and this powers turbines. And geothermal sources can be found very close to geysers, hot springs, volcanoes, and so forth. Because there's so many active volcanoes and volcanic activity in around Iceland, a good chunk of their energy is geothermal energy. But among the most active sources and most active uses of it is the United States, Mexico, New Zealand, Japan, again, as well as Iceland. And then good old-fashioned wind power. Very cheap and efficient. May see more and more is wind farms, especially go in places like West Texas and portions of Oklahoma. There's miles and miles of nothing but miles and miles. What you have there, though, is a lot of wind. So might as well put it to use. So put up these giant windmills that produce a lot of electricity. You see them off the sides of highways often. By 2002, the United States, 17% of electricity used was through wind power. California used about half of the nation's wind power, followed by Texas. Germany is the leading producer of wind power, about 1/3 of the world's supply at some point. In fact, sometimes the wind's right and the sun's right. Most of their energy now, here in the 2020s in Germany, comes from alternative sources like solar and wind power. And in Denmark, 16% of wind, 16% of their power comes from wind power. And certainly there are other sources beyond this. A little engineering know-how, a little imagination, no telling what we can come up with. But remember, natural resources, so many resources, so many things we can use. But it all comes down to choice and comes down to how we use them and what are the payoffs. What is the cost of using a certain resource? What is the cost of not using it? What's the cost of using certain different kinds of energies? Because man-made problems in the world with pollution, energy use, energy conservation, and so forth, it's a matter of choice. We do have choices in this matter. We're not helpless. We can solve problems. It's a matter of the will to do it and the imagination to do it. And all that comes down to understanding what you know about the earth, where its resources are, what can be used as a resource, and how it can be distributed. It's a world we all share. It's a world we all have a say in. So use the world wisely. That's it.